Hello again, friends. Welcome to the next lecture in the series Cosmological Perturbation Theory. In this video, we'll look at the gauge transformation of scalar quantity f. In the last videos, we have looked at the gauge transformation in general first. We derived some helpful expressions that we will be using in transformation of tensor, vector, and scalar from one gauge to another gauge. Then we looked at the transformation of a tensor of rank 1 and tensor of rank 0 Now next we'll look at a very simple transformation, which is the transformation of a scalar quantity f from one gauge to another gauge. So we have delta f perturbation in gauge 2. How is it related to delta f perturbation, which is in gauge 1? And remember that in the final expression, we don't write caret on top of gauge 1 just to simplify the notation. But when we are doing calculations, we'll put caret on top of gauge 1, and in the final result, we'll drop caret to simplify the notation. Okay, so let's start with our as I mentioned in my previous lectures, that the starting point is this relationship f at p tilde say this is in gauge 2, so I can write this as f tilde. So value of f in gauge 2 at point p tilde minus value of f in gauge 1 at point p caret. And this expression we looked at, we introduced this when we introduced the perturbation theory, gauge transformations in perturbation theory. And we used this starting point in our previous transformations. So it's the same starting point. The value of f in gauge 2, tilde means gauge 2, at point p tilde minus the value of f in gauge 1 at point p caret. P tilde and p caret, they have same coordinates in their respective gauges. P tilde coordinate in f tilde gauge is same as p caret coordinate in caret gauge, and tilde is 2 and caret is 1. So this is given by the value of perturbation in gauge 2 minus the value of perturbation in gauge 1. Now, in order to find how these two are related, we can write this as this. So to get an answer to this question mark here, we need to simplify the right hand side as much as we can. Now, what is f tilde p tilde? This is in gauge 2. Let us bring this at this point, at p tilde point. Let us do the gauge, let's do the transformation at the transformation of this scalar f tilde at the same point p tilde from gauge 1, from gauge 2, f tilde is in gauge 2. Let us bring it from gauge 2 to gauge 1 at the same point p tilde. And note that f tilde is scalar. If f tilde is scalar, from the tensor transformation rules, which we have seen in general relativity and which I talked about in my lecture 1. Tensor transformation rules, they are at same point. So when I am doing the same point transformation, I'm transforming a quantity f, which is you can say this is tensor of rank 0, 0, or it is a scalar. So scalar quantity, when you transform at the same point, remember, at the same physical location in the 4-dimensional space-time, same point p tilde, when you transform from one gauge to another gauge, the value of scalar is the same. So this will be f caret p tilde. This is f caret p tilde. So I can write this as caret we have also seen in our previous lecture how the value of p tilde and p caret points are related in one single gauge. So here, if we have to look at p tilde and p caret values of the scalar f in gauge 1, both the values, then they are related according to this expression which we have seen in our previous lectures. So value of, and I will put all the relevant equations in the review sheet, which I will share in one of my future videos. So you will find all the helpful equations which I am using here, which I have derived in my previous videos. You can find them on the review sheet. So value of p tilde and p caret, they are related according to this expression. This was derived in one of our last videos. So tilde, p tilde value is equal to caret value, p caret value minus f bar gamma xi gamma. So now we can simplify this. We can say this becomes this. And if I write here like this, so tilde is equal to value of the perturbation, scalar perturbation delta f in gauge 2 is equal to value of scalar perturbation in gauge 1 minus f bar derivative with respect to gamma xi gamma. And I can drop the caret sign. So the final expression becomes this. And remember that the background quantity does not depend upon x, y, and z coordinates. It is only a function of conformal time eta. So its partial derivative with respect to x, y, and z coordinates will be 0. So when we contract on gamma, only the 0 component survives. So this is the expression for scalar transformation from gauge 1 to gauge 2. Now we are going to see how a vector quantity f alpha is going to transform from gauge 1 to gauge 2. And this is our starting point. The value of f alpha in gauge 2 minus its value in gauge 1, the value of perturbations, difference in perturbations between the values in gauge 1 and gauge 2 is equal to the difference in the perturbed quantities at the same coordinates, which is p caret in gauge 1 and p tilde in gauge 2. And I'm repeating this again and again because this is important, and also because that some of the viewers might be watching it for the first time. They have not watched the previous videos in which I have explained that p caret and p tilde, they have same set of coordinates in their respective gauges. So when we look at them, they physically they are not the same points, they are different points. So when we look at them in one gauge, they have different coordinates, but the way we have constructed the gauge theory, they have different set of coordinates in one gauge, but same set of coordinates in their respective gauges. So the coordinate of p caret in gauge 1 are the same as the coordinates of p tilde in gauge 2. Okay, so now let's see what we can do here. So we have this. Now I can write, I can do transformation of f tilde alpha to f caret alpha at point p tilde using the tensor transformation rule at one given point. So this will become, I can write here x, this is tilde, this will become mu caret, and can say let me get the notation right. So previously I put tilde on top of the coordinate, so I think we can do the same here. So I can put this tilde here. So this is gauge 2, and then I can put the caret here. Caret. Then this is f mu, and this will be mu at the this I am bringing to gauge 1, so this has to be in gauge 1. I'm transforming the value of f alpha from gauge 2 to gauge 1. So this is gauge 1 at point p tilde, and if this is gauge 1 mu caret, and then mu caret is here, and this is alpha caret, this guy, okay. So we are doing a gauge transformation using this tensor transformation at a given point. Now this can be written as, sorry, caret caret here, and this is tilde. This is tilde. This is tilde. Now the value of this we have seen in our previous lectures, and you can find it on the review sheet also, which I will share in my future videos. So this is tilde on top and caret bottom. Tilde top caret bottom is this. Tilde top caret bottom. Tilde top and caret bottom. So alpha top, mu bottom. This is mu. Skip mu. This is mu. All right. So next would be simplification of this. We can write this value of f mu caret p tilde in terms of f mu caret p caret. Same strategy that we used for our previous tensor and scalar problems. Using the same strategy. I can write this as f mu caret p tilde. This is f mu caret p tilde will be, let me write this as this, and f mu caret p tilde will be replaced with this thing. Replaced with this thing. But we have not alpha but mu. And using this. Okay, so everything looks good so far. This is good. Okay, now delta alpha mu, there are total 4 terms, and this xi alpha is a very small quantity. Its derivative with respect to mu is very small, and here xi gamma is very small. So this multiplied by this is a second order term. So let us remove this. So this there will be total 4 terms, and the fourth term will be gone. Okay, let's write one by one. Delta alpha mu with respect to f mu caret p caret. Okay, this will come here, and this will come here. Okay, then delta alpha mu will come with this guy. Third term is this. Something not right with the indices. We'll fix it. Something not right with the indices here. Yeah, I got it. This has to be f bar mu. This is f bar mu. Okay, so let's now fix the master. Okay, the master is gone. Now let's copy it here. Oh my god, this guy. Okay, yeah, mu alpha 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 alpha. Okay, this is good. So delta alpha mu with f mu caret p caret, xi alpha mu with the f mu caret p caret, two terms, third term delta alpha mu with this guy, and fourth term is second order. Xi alpha mu with this multiplied by xi gamma is the second order term that we drop. Okay, now what next? Let's now leverage the power of Mathematica, copy paste, and I can simplify the first term, delta alpha. This is now alpha. Basically, this is also f in alpha caret coordinates. Just fixing the notation here. This is also here like this, and here also like this. Just the notation, fixing notation here. So this minus this is gone. What is left now? What is left is this. What is left is this, and then after 1 second this is left, and now I don't need to put p caret here. What is this? 1 second. Yeah, because I want to write everything in terms of the background coordinates. So this I can simplify by writing b f bar mu plus the some transformation vector So this is the transformation of a relationship between the background value f bar mu at point P and f in the caret gauge at point P caret. So they are related according to this relationship. And now kappa mu is a transformation vector. Its values are very small. Its value is very small. So when xi alpha mu is multiplied by kappa mu, it is a second order term which we can drop. So this would simplify to this. Simplify to this. Would simplify to this. This. Anything else? Yeah. Mu. And this will become alpha. And this delta alpha mu is gone. Okay, so we have xi alpha with respect to mu, f bar mu, minus f bar alpha with respect to gamma, and then xi gamma. Any simplification here? Yes. F bar alpha is a function of eta only. It does not depend upon x, y, z. So when we contract on gamma, the partial derivative of f bar alpha with respect to x, y, and z will vanish, will be 0. Only the eta term will survive, 0 and 0. I think that's as far as we can simplify. It's equal to this. So the perturbation transformation, the vector perturbation transformation can be written as this plus this. And finally, we can drop the caret sign. So the one without caret is gauge 1. And the one with tilde is gauge 2. Perfect. Now, can we write the coordinates, the components? So we can write 0 component and I component. Let's see, the alpha equal to 0 component. 0 component. Zero component. What is a 0 component here? 0 component is, first thing is copy, second thing is paste, third thing is replace alpha with 0. Okay, this is 0. Okay, and then this is 0. Okay, any simplification here? I don't think so. I think that's it. So now the I component. I component, step number 1 is copy. Step number 2 is paste. Step number 3 is alpha, replace with I. And what is f bar I 0? This will be 0 because f, oh no. What is f bar I? F bar I is not with respect to 0 is 0, but f bar I is 0. This we can easily see. F bar mu is not 0. F bar mu has 4 components: f bar 0, f bar x, f bar y, f bar z. So f bar mu is not 0 because it has non-zero component, which is f bar 0. But f bar I is 0. This is a 0 vector. Why is it a 0 vector? Because f bar I is in background space, and if you want to respect isotropy, f bar I, whatever vector it is in the background space, there is no preferred spatial direction. Whatever vector it is, whether it is velocity vector or whatever vector, any vector quantity in the background space does not have any preferred spatial direction, which means it has values like direction wise, like f bar vector is randomly distributed in the space. So somewhere it is in one direction, somewhere it is in another direction. So there is a random distribution of f bar such that average of this vector, and what f bar represents is the average value. The average value of this vector is 0. For example, let us say that we have a velocity vector. So velocity vector, there is no preferred direction, or any vector f alpha, there is no preferred direction. It can have this, somewhere it is 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 this, somewhere like this, somewhere here, somewhere here, somewhere here. So there is no preferred direction. And what we are taking in the background is the average value of this, and the average value of, sorry, not f alpha, but fi. Because f alpha has 4 components. One is f0, and then the 3 special components fi. So fi average value, this, and this. So the average value will be 0. This is null vector. Okay. Therefore, this would simplify to copy and paste. Where is paste? Here. Okay, so this is the 0, 0 component transformation of vector perturbation, and this is the I component transformation of vector perturbation. Yeah, I just realized that we can go one step further in both of these scenarios, because f bar I is 0. So when you contract on mu, only the 0 component survives here in the f0 transformation. So this can be simplified like this. Only the 0 component survives. This is 0, 0. And here also, when mu contracts, only the 0 component survives. So this can also go one step further. I component disappears, and this will be 0 and 0. Okay, that's it, guys. So I will put all the important formulae that we derived here, such as the expression for delta f I and 0 component transformation, I component transformation, and the scalar transformation. I will put all these relevant equations in the review sheet, and when we are going to do the next topic, which is metric transformations, we will be needing all of the relationships that we derived here. So yeah, that's for the next video. We'll talk about metric perturbations in G alpha beta. And for today, this video, that's all. Thank you very much. Thanks for watching. Continue learning, continue experimenting, continue researching, and continue spreading the knowledge. Physics is fun. Thank you. Bye-bye. See you next time.